Hi, my name's Lucas. This is my project 2.4.3, the SAR ADC completed. So it's worth to note, before I start off, that this design is based off a schematic that was originally created by Dr. Yamada. So he deserves some major credit because this project really would not have happened without him. And his original project description is in the description. So he deserves some major credit because really this project would not have happened without him. So in this video, I'll be demonstrating my own working SAR ADC. I'll go over some oscilloscope images I took, and then I'll explain how the circuit actually works. So you can see here, really the only input on this is the circuit's potentiometer. So here it's at 5 volts, and as I turn it down, the final output, these LEDs, gradually starts to decline. So what this circuit does is it takes this analog voltage from whatever the potentiometer is, and it pretty much guesses, it's an educated guess, but it guesses what the voltage is, and once it finds it's as close as it can possibly be, it displays it on these LEDs over here. We can confirm that this circuit works. I don't have an oscilloscope on me, but I'll show some images later by just turning on this DMM right here. You can see this is plugged into the output of this R2R ladder, and you can see as I turn the potentiometer further back, the DMM, the value of the R2R ladder decreases with it. So you can see here the max of 4.16 volts. Not sure why it's not 5, but see here all these LEDs are on the max, and as I decrease it, the LEDs slowly start to turn off, and the DMM also decreases. So this is actually a 7-bit binary number, and we can convert this back to voltage using some pretty simple calculations. So here's just a simple Google Doc, but there's a screenshot of an example of a voltage that was set. You can see here on the upper right corner of the picture is the output LEDs, which is just a 7-bit binary number, with the most significant bit being to the far right here, so value of 64, and that's on right now, and the least significant bit, value of 1, being to the far left. You just add them all up, 64 plus 4 plus 2 plus 1, to a value of 71. So this binary value is 71. And what you want to do to convert this to a voltage, try to get around 2.6 volts, is to divide it by the maximum possible number. So this is a 7-bit SAR ADC, so you divide it by 127. If all these were on, it would equal to 127. So 71 divided by 127 is equal to 0.559. This is still not really 2.6, because what you want to do is take 0.559 and multiply it by the supply voltage, which is 5 volts, right? Multiply it by 5, and you get 2.7. And that is pretty close to a 2.6. It's not exact because it is an approximation, right? Because it's only 7 bits, it can't be super precise, and there's still, this binary value is not exactly 2.6, and it really never will be 2.6. And because of this, you can see here this recording here, that there's some flickering in the LEDs, especially in LEDs of lower value, because here this is the lowest 2 value LEDs that are really flickering, and this is because the ADC is approximating directly above then directly below the analog value, and because of the tolerance, right, the least valued bit is 0.039 volts. It really can't get any more precise than that, so it approximates directly higher than directly lower than the analog voltage, and that's why you get this like flickering. So here I'm not even touching the potentiometer, and it's still flickering. I took some oscilloscope images. First, the yellow is the measured analog voltage, and the green was connected to the R2R ladder's output. I added these numbers here for reference, but you can kind of see the SAR DAC's kind of thought process, you could say. Its first step is to turn on the most significant bit of 2.5 volts, which is less than the analog voltage. So it turns on the second bit, which is now more than the analog voltage. So it'll turn off the second bit and turn on the third bit. It kind of goes throughout this process, kind of zeroing in on the analog voltage just with its only data being whether the R2R ladder's value is higher or lower than the analog voltage. And you can see as time goes on, it kind of zeroes in on the analog voltage. And it's also worth mentioning, I think, that this happens in like fractions of a second too. Here, this is Dr. Yamada's original schematic. That's what I was talking about earlier. So here's some of the stuff we already created, like the clock circuit in the top left, and the R2R ladder and sample and hold and comparator in the top right. You can see here, instead of dip switches, there's now AND gates connected to this R2R ladder. On the actual breadboard, these AND gates are located right beside the R2R ladder. It's at the bottom left of the circuit board. Just a reminder, AND gates, they only output a true if both of their inputs are true. Anything else and their output will be false. But anyway, back to the actual circuit diagram. You can see if you actually follow the traces, the inputs for the AND gates actually connect to 3 different places. But first I'll cover these little small square looking things. These are actually 1-bit D-type flip-flops. And I have 4 ICs for each of these because there's 2 flip-flops per IC. And there's 7 to match the 7 AND gates. The way these work is they work on the rising edge of a clock signal. So on either a rising or falling edge, the data input, you can see D, will equal the Q output. But in between clock signals, the Q output will remain constant. Here's an actual pinout diagram of one of these 1-bit D-type flip-flops. See, each side of the IC accounts for 1 flip-flop. Now, across all 7 flip-flops, each D input pin is actually tied together and attached to the comparator output. Additionally, each set pin is tied together. So the flip-flops attached to the AND gates through their clock and output pins. However, they do it in a bit of a weird way. You can see there's a corresponding flip-flop for each AND gate, right? There's 7 flip-flops and 7 AND gates. On the flip-flops, the Q output is tied to their corresponding AND gate, but their clock signal is actually tied to the next AND gate. This image kind of shows it. However, this will leave the last flip-flop's clock signal empty and the first AND gate's input pin empty. But I'll go more in depth on those 2 connections in a little bit. Also, the 4 ICs for these 7 1-bit flip-flops are in the middle breadboard of the prototype. Moving on to the last 2 chips in the circuit, these are HC 273s. They're octal D-type flip-flops, and unlike the previous ones, they can control up to 8 bits and all work on the same clock signal. So this circuit works on the same rising and falling edge as the previous 1-bit ones. So these are attached to the 103 μF oscillating circuit that we made before, and this is actually oscillating so quickly that the chip updates basically instantly. The first one I'll go over is this one to the far left. Outputs to the clock signals on each 1-bit flip-flop. However, something that's a bit weird is that each input is tied to the previous output. See here that like D7 is tied to Q6. The first input, D0, is actually tied to that first AND gate that I was talking about previously, and that entire line is tied high. Additionally, Q7 is tied to the clock pin on the next HC273, and that signal is knotted and goes back into its own clear pin. Also, Q6 is tied to that last clock pin on the 1-bit flip-flop that I was talking about before, and that entire line is tied to the hold part of the sample and hold circuit. So now the HC273 to the right, so it's much more simple. It just takes its inputs from the Q of the 1-bit flip-flops and outputs to the 7 red LEDs. On the actual prototype, all these chips are located on the upper breadboard from left to right, the clock signal, the first 273, then the second 273, then finally the output LEDs. That was my video on the SAR ADC completed. Thanks for watching.